Welcome to this explainer. So, if you're building modern applications, you're inevitably faced with this really tricky challenge, choosing the right database. And let's be real, if you've glanced at the landscape lately, it is totally overwhelming. You're just bombarded with all these buzzwords: NoSQL, relational, document, graph, schemaless. It's a lot. How do you actually make sense of it all without just falling for the hype? Well, today we're going to unpack the evolution of data interconnectivity, the models we actually use to store it, and the languages we use to query it.
Which brings us to a really fascinating question. After decades of relentless innovation in software engineering, why on earth are we still juggling so many different types of databases? Why hasn't the tech industry just built one ultimate universal system that literally does everything perfectly? It seems like it would just make everyone's life so much easier, right? But when we actually look at the data itself, we realize it comes in vastly different shapes. Forcing all your data into a single model, it's basically like trying to jam a square peg into a round hole.
So, because there's no single perfect database, the modern standard has actually become this thing called polyglot persistence. And what's super cool about this concept is that it openly acknowledges that different parts of even a single application have completely different needs. You might have one feature that demands massive scale and a really flexible structure, right? But then another feature requires incredibly complex, tightly bound relationships. So instead of compromising, modern architectures just use different storage technologies right alongside each other. You essentially match the database to the specific shape of your data.
All right, let's dive into our first section, the object-relational mismatch, or what happens when objects meet tables. Let's start with a classic developer headache, the object-relational mismatch. Think about a LinkedIn profile. Let's use Bill Gates as an example here. In your application code, his whole impressive resume is probably just one neatly organized object. But to store it in a traditional relational database, that data gets violently fragmented. We literally shred it across multiple tables. You've got a users table for the basic info, sure, but then you need a totally separate table for positions, another one for education, and another for contact info. And to put his profile back together, the database has to execute all these multiple joins. This whole disconnect between your object code and the database tables, that's known as an impedance mismatch. It basically forces you to use this awkward translation layer every single time you want to read or write data. Now contrast those messy, fragmented tables with this alternative, the document model. This is the exact same profile, but represented as a continuous JSON tree. And wow, notice how elegant this is for this specific shape of data. A resume is mostly a self-contained document, right? By storing it as a JSON tree, you get incredible storage locality. The entire profile can be fetched in one single go, no expensive database joins required. Plus, document models typically use a flexible schema-on-read approach. That means you don't have to rigidly declare every single field up front like you do in a strictly structured relational database.
Okay, moving on to section 2. Are we repeating history? The cyclical nature of databases. So looking at how incredibly easy that JSON document was, you might be thinking, wow, newer NoSQL document databases finally cured those clunky relational models. But are we actually just repeating history here? Let's trace this back a bit. Way back in 1968, IBM released IMS. It was this enormously successful database actually used for the Apollo space program. IMS used a hierarchical model, which, and this is wild, looks almost exactly like the JSON trees we just talked about. It worked beautifully for self-contained records, but it struggled heavily the minute data started interconnecting. To solve those limitations, Edgar Codd proposed the relational model in 1970, and it completely took over the world. Fast forward to 2009, and the NoSQL movement is born, essentially bringing back that hierarchical tree structure via document databases to solve the rigidness of relational tables. We are literally having the exact same architectural debates from the 1970s.
Which brings us to section 3, the relational comeback, scaling complexity and many-to-many data.
So why on earth did the relational model take over in the 70s, and why is it still absolutely fundamental today, even with the rise of NoSQL? Well, it all comes down to what happens when data interconnects. Let's go back to our resume example for a second. Imagine you want to add a simple, highly practical feature. Instead of having users just type Microsoft as plain text in their experience section, you want to standardize it. You make Microsoft a clickable entity, like a standardized drop-down option. This avoids spelling errors, lets you track data consistently, all that good stuff. But the moment you do this, you've introduced complex relationships. You suddenly have many people working at one company, creating a many-to-one relationship. And here is the absolutely crucial point. as you start standardizing organizations, schools, recommendations, that isolated JSON document we loved so much earlier, it instantly transforms into a massive, complex web of cross-references. This is a highly interconnected environment. Document databases traditionally struggle big time here because they really lack strong support for database-level joins. So if you try to force this tangled web back into isolated documents, you're either duplicating massive amounts of data or you're forcing your application code to manually stitch everything together with multiple queries. Honestly, it's an absolute nightmare for both performance and developer sanity.
And that brings us to a pretty clear realization. Document databases aren't inherently better or worse than relational databases. They really just serve fundamentally different data shapes. If your application relies on isolated trees of data where you absolutely need flexible schema on read, then document models are fantastic. But if your app requires strict schema on write integrity and actually thrives on structured joins to navigate interconnected data, well, the relational model remains completely unmatched.
Next up, Section 4, the graph data matrix, when everything connects to everything. But what happens when we push that interconnectivity to its absolute limit? Like when many-to-many relationships aren't just common, but they're literally the defining feature of your data. In those cases, relational tables actually become just as clunky as documents. And in these scenarios, it becomes incredibly natural to use a graph model. Graph models strip everything down to just two basic concepts: vertices, which are your entities, like people or locations, and edges, which are the relationships connecting them. Think of a massive social media network where millions of people are connected by who they follow, or a mapping application that's calculating the fastest route through an insane web of intersecting roads. Graphs are purpose-built to traverse these massive interconnected webs super efficiently. All right, Section 5, languages for querying data. Basically, how we actually talk to our databases. Up to this point, we've talked entirely about storing data, but how do we actually get it back out? This difference fundamentally boils down to imperative versus declarative query languages. If you're writing imperative code, like a standard JavaScript root, for example, you have to tell the computer exactly how to do its job. You write the logic to iterate through a list of animals, line by line, check if each one is a shark, and then add it to a new list. But SQL, the language of the relational model, is declarative. You simply tell the computer what you want. You just say, hey, give me the animals where the family equals sharks, and you let the database figure out the rest. It's just an incredibly elegant way of hiding all those messy implementation details from the developer. Let's expand on why declarative languages like SQL are just so incredibly powerful. The true unsung hero here is the query optimizer. Under the hood, the database engine looks at your declarative request, scans all the indexes it has available, and automatically determines the most efficient access path. Because the database handles the how, it saves developers a massive amount of time. You can add new indexes or even completely overhaul the database internals, and your query logic never has to change. Plus, it naturally lends itself to parallel execution across multiple CPU cores, mostly because you haven't forced the computer into a strict line-by-line set of instructions. Now, there is a really interesting middle ground worth mentioning here, especially when we talk about NoSQL and big data, and that's MapReduce. Popularized by systems like Hadoop and MongoDB, MapReduce acts as a bit of a hybrid. You write imperative snippets of code, specifically a map function and a reduce function, often just standard JavaScript. But then the database framework totally takes over the complex execution orchestration. It handles moving the code to the data, paralleling it across a massive cluster of machines, and then efficiently bringing all those results back together. Okay, we have covered a tremendous amount of ground today. So, to really empower your architectural decisions moving forward, here is your definitive cheat sheet. If your data is shaped as one-to-many, self-contained trees, and you really need schema-on-read flexibility, go grab a document database. If you're dealing with simple, many-to-many relationships that require explicit schema-on-write enforcement and robust joins, the relational model is absolutely your best friend. And if you're dealing with highly interconnected, web-like network data, you definitely need a graph model. Understanding this matrix, it's literally the key to mastering polyglot persistence. I want to leave you with this really provocative thought from computer science pioneer Alan Kay. He noted that computing is like pop culture. It lives in the present and often holds a total disdain for history. We're always chasing the newest NoSQL database or the latest trendy buzzword without realizing that we're often just reinventing the hierarchical models of the 1960s. By actually understanding the cyclical history of these data models and the fundamental trade-offs between them, you can finally cut through the hype. You stop looking for the perfect database and you start looking for the right tool for the exact shape of your data.
So think about the data in your current project. Are you genuinely using the right model, or are you just using what's popular right now? Thanks so much for joining me on this explainer, and keep learning.